So now we'd like to look at linear constant coefficient differential equations and how we can take Laplace transforms of those to arrive at rational Laplace transforms for transfer functions. So here we're kind of describe a very important class of systems, and those are systems defined by linear constant coefficient differential equations. So we'd like to be able to convert these linear constant coefficient differential equations, which from now on I'm going to call LCCDEs, because it's a mouthful otherwise. So LCCDEs, we want to take those and convert them into rational Laplace transforms, and then find the impulse response, and then use the known transforms essentially to simplify returning back to the time domain from the impulse response to get the impulse response. So probably the first place you saw Laplace transforms was in the class on differential equations, and they're usually taught as a simple technique to solve LCCDEs, especially with zero initial conditions. Okay, so suppose we have a system with an input-output relationship given by a linear constant coefficient differential equation. So here we have a second-order derivative of y, a first-order derivative of y, then first-order derivative of x, and then x. So the recipe is simple. We just convert d dt goes to s, and x of t, y of t, these go to x of s and y of s. And that's really just a kind of letter-by-letter substitution, if you like. And we're leveraging this property that when I take the derivative of a time domain signal in the Laplace domain, I'm just multiplying by s. So we just pull off the coefficients from this differential equation and replace the derivatives with powers of s. So you get 5s squared minus 3s plus 1. And we get minus s plus a half. And so we get the y of s and then the x of s. Those things factor out. And then we just divide y by x to get the transfer function h. And this is the transfer function that transfers you from the input signal x of t to the output signal y of t. And it has you can see here that it's a rational Laplace transform. So in general, if you have a system defined as a bunch of derivatives of y with some coefficients equals a bunch of derivatives of x with some coefficients, you can just convert all the derivatives to s's, powers of s, and keep the coefficients. You'll get two polynomials in s. So you're going to get a polynomial in s multiplying x of s and a polynomial in s multiplying y of s. And then when you cross divide to get the transfer function, you're going to get this rational Laplace transform, And then what you can do is, hypothetically at least, factorize this Laplace transform into a constant times a product of zeros on the numerator. So we can call these zeros, say, at alpha 1, alpha 2, alpha k, and similarly beta 1, beta 2 up to beta l. So here are the poles and the zeros of this transfer function. So let's do a little example. So let's look at a causal system, and causality will be important when we try and find the time domain signal, defined by the following linear constant coefficient differential equation, LCCDE, right? So we have a second derivative of y, a first derivative of y, we have a first derivative of x and an x. Converting all the derivatives to s, powers of s, we get this. And so we get the transfer function is s minus 1 over s squared plus 6s plus 13. Okay, so now we need to find the pole zero diagram for this transfer function and try to understand what's going on. Okay, so we're going to find the pole zero diagram. So we've got a 0 at s equals 1, right? So 0 at s equals 1. And then we have to use the quadratic formula on the denominator. So we get minus 6 plus minus 6 squared, which is 36, minus 4 times 13, which is 52. 36 minus 52 is 16. Square root of 16 is 4. So this whole thing is equal to 4. So we get minus 3 plus minus 2j. So that was a little bit fast, but that's just algebra. That's just high school algebra for you. Right, so we have two poles. We have poles at minus 3 plus 2j and minus 3 minus 2j. And then we have a 0 at 0. So this is what the pole 0 diagram looks like. And now we want h of t has to be causal So it has to go from, so the ROC is a right half plane. Right, so it has to go from something from the from the rightmost pole to infinity. Here the poles have the same real value. Okay, so we know the system is causal, so we have this following ROC. So how do we get back from the poles and zeros and the pole zero diagram back to the time domain signal? That's the question that we want. And so maybe we can use some Laplace transform properties or known Laplace transforms. So we got to look at the denominator first in order to understand how to do this, right? So here's our h of s, and then you have to kind of squint at it and say like, well, it's an s squared. It's got complex roots. What do we know about pairs of conjugate pair of roots here? So remember, these are conjugates of each other. So this is a conjugate pair of roots. So what do we want to do? Well, okay, so we can try to pull a square out of it, because we know that we've seen things where with Laplace transforms with 1 over s plus something squared, right? And those corresponded to like exponentials with cosines or something like that, and we'll see on the next slide what that looks like. So let's first try to pull out a squared term. So we have s squared plus 6s, so we'll get that from s plus 3 squared, but then the 3 squared, the last term, 3 times 3 is going to give you a 9. We take away that 9 from that 13 and we're left with 4. So we can write this as s minus 1 over s plus 3 squared plus 4. So now where do we go from here? So we need these transform pairs, and we can derive this cosine same way that we did the sine before, or hopefully you did it as a sort of try it yourself exercise earlier. So we have the following transform pairs. A decaying exponential times a sine times u of t is going to give you omega naught over s plus a squared plus omega naught squared. A is the rate of decay of this exponential, and then omega naught is the frequency of this sinusoid. And similarly, if we have a cosine, we have e to the minus at times cosine omega naught t. We're going to get s plus a in the numerator this time instead of omega naught, but with the same denominator. So here we have omega naught equals 2 if you look at the previous slide. Because why? Because we have omega naught squared equals 4, so omega naught is equal to 2. And then we have a is equal to 3. And how can we see that? Well, let's we have this s plus a squared in the denominator, and we have an s plus 3 squared in the denominator. Right, so this 4 and this s plus 3 gives us omega naught in a. And then we look at this and we have to write it in terms of terms that look like this, these two terms here, this sine and this cosine. So we pull out an s plus 3 over s plus 3 squared plus 4. So that'll give us a cosine term. That's going to give us this cosine term, e to the minus 3t. Here's the 3 comes from here. And then cosine 2t, because this is omega naught squared, u of t. And then in order to make this s minus 1 in the numerator, we have to subtract 4 over here. So that's actually 2 times omega naught. Omega naught is equal to 2, so 4 is equal to 2 times 2. And again, we have e to the minus 3t, and now sine 2t, u of t. Right, so here's my impulse response that for this causal system based on a linear constant coefficient differential equation. So just taking a step back and looking at the steps that we took here, given a linear constant coefficient differential equation, first you convert all the ddt operations into multiplication by s, and then generate the Laplace transform h of s is equal to y of s over x of s. So this is a transfer function. And then we want to find the poles and zeros and then plot the pole zero diagram. And then we want to use the pole zero diagram to choose an ROC based on what we want out of the system. Do we want it to be causal? Do we want it to be stable, etc.? And then we're going to invert the rational Laplace transform using partial fraction expansion and known transform pairs, so maybe or and transform pairs. And that's the steps that you take, starting from an LCCDE plus a description of what kind of system you want, how you get back to the impulse response, right? And so this is a important skill to develop, or like be able to sort of go through this process. It really will cement sort of all of the concepts that we've seen so far kind of put together. So as a result, I think you should try a couple examples. Here are a bunch of examples for you to do of LCCDEs. And let's assume that all the impulse responses are causal first. Try all three. Then try and see what happens if you say the impulse response is anti-causal, or the impulse response is, and then you might want to ask if the system is stable, and so on and so forth. These are questions then you can ask yourself to try and integrate some of the knowledge that we've been gaining so far in the last few presentations.